Okay, so we'll have searching and sorting algorithms. Perhaps next semester I will get around to updating this into a different format. This lecture is straight from an old McGraw-Hill textbook. Uh, it's okay. Their images are nice. That's why I haven't gotten around to updating it. There are some typos in there I've mostly corrected. But you know, Java is Java. Even though this was written, the book itself is from 2005. At this level, you know, Java is Java. The syntax for the basics haven't really changed. So what we're going to cover, two things, searching and sorting. So I'm just going to skip ahead for a minute. And we'll go into Paint. Am I sharing the screen? I hope I'm sharing the screen. Yeah, good. Okay. So searching is trying to find data within a large array. Okay, so for example, suppose your array is phone directory for Chicago, which is large. Okay, and you want to find the phone number of, I don't know, Susie Jones. Okay, you met her at a party and you want to find her number and you got to give Susie a call. Okay, so that's an example of searching, right? Trying to find something within an array. We'll talk about algorithms for that. Sorting is trying to, or I shouldn't say try, is arranging the data typically to make it much easier to search. Okay, so anybody ever actually use a physical phone book? That's good. No, you have? Explain it. How is this? Yeah.
Well, the one that I had, it was just like basically like everybody's like name and their address and then their actual phone number like within a city. Like it was like the county, I think. So it was like maybe like 250,000 people. But, yeah.
Okay. So that is I will accept that. That is a good description. It is a large book full of records. Every record in the phone book is a last name, first name, address, phone number combination. Okay, and we're skipping the part of, you know, there may be businesses in there as well. We're just talking about personal phone numbers. Now, suppose I tell you to look up Susie Jones in that phone book. How would you do it?
Well, it's sorted alphabetically, I think, by last name.
It's sorted alphabetically by last name, meaning what do you do? What?
Let's go to J.
Go to J, right? And if you overshoot a little bit, if you go to K, you back it a little bit till you find JO. If you undershoot it a little bit, you start at, say, JI, you roll it forward a little bit to get to JO. Eventually you find the page where things are on, and eventually you converge to the number of Susie Jones. All right, so we're all comfortable with this concept of a phone book? Yeah, so once upon a time, we were very glad to have them. Okay, now, suppose I twist the thing up a little bit. Suppose you don't know Susie's last name. Suppose you just know her first name and that she lives on, I don't know, 123 Main Street. How would you go about finding Susie's number? It's in that phone book. How would you go finding it? You don't have the last name.
You go based on the address?
Yeah, okay, but how would you actually go about physically doing that through the book? Yes, you could go by the address. You would have to well, suppose this is a physical phone book and you're not going to resort it. What would you have to do? You got to go through every single entry, right? It's in there. You will eventually find a Susie who lives at 123 Main Street, possibly more than one, right? She could live with, I don't know, her mother or her daughter, also named Susie. I don't know. Okay, so that's kind of the problem. So, data that has been indexed along a particular variable, like last name in a phone book, is much easier and faster to search than data that has not been indexed on a search variable, like address in a phone book. Okay, then you have to search through every record to find a match. Okay, so these are the two things we're dealing with. First of all, you have a large pool of unsorted data. The first task is to sort it in some way that makes it easier to search. And the second part of the algorithms are actually algorithms for how you go about telling a computer to do the stuff that we as humans fairly intuitively understand how to do with phone books. Okay, that's what today's all about. Are we good? Questions? Would anyone like to know more? Well, you're going to learn more anyway, so let's just do it. Okay. All right. So if you have a big pile of data, one of the operations you need is a search routine to locate things quickly. Okay. And the way we're going to describe this, you have an array of data and you want to find a particular value X as an array element, and you need to return the index where that value is stored. All right. So imagine if you have a large array full of credit card information, right? And it's somehow sorted by credit card number. What you could do is say, okay, I'm going to type in a credit card number, and once I can find the list, maybe that record will also hold the security code, so I can look up, yeah, if I find that record, you know, that matching number, I can also find the security code, I can also find the owner and the address and the zip code, all that other stuff, okay? And if you know the index of that array element, you'll be able to find all those things. Okay. Now, the best algorithms in this case are the ones that require the least work to do it. And here they say the fewest comparisons, so the fewest checks. So imagine if you have a database that has 1 billion records, right? 1 billion credit card records. Searching the entire thing would take 1 billion comparisons, right? You'd have to check the first one. Is that a match? No. Check the second one. Is that a match? No. All the way on to 1 billion. If you do it the other way, like we do with the phone book, it requires many, 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 many fewer operations. So we're going to discuss all that. All right. So first one is the linear search. Okay, so, but we'll get to that in a second. So suppose we're looking up the number 45. You can think about this array holding whatever data you like, but they'll keep the numbers simple, make the, make it easier, keep the array small and make it easier to visualize. So suppose we're looking for the number 45. We can eyeball through that array of 9 elements and say, hey, there's no 45 there. Okay, we can very easily see that and say, yeah, nothing's found. Likewise, with a successful search for, say, the number 12, we can easily eyeball that and say, oh, we have that. We're going to return a 4, right? And just like with our string method index of, the not found code is probably going to be a -1 since that's never a valid array index. Okay. So the first one, it's very easy to understand, is the linear search. The linear search, you start at index 0, you search through every index in the array until you find what you're looking for. If you find it, you return the value. If you go through the whole array and you don't find it, ta-da, you're done. You return the failure code. Okay, and this is some simple code here that does that. That does a linear search. It accepts an array, it accepts a search value, and it will scan through the array until it either finds a match or it's looked through every element in the array. Now, for the exam, you don't have to know how to, you will not have to replicate code like this. There was already a question that was kind of like this on the second exam anyway, right? If you're looking at, that's basically what some of those things expect you to do. Do a simple linear search on an array, right? So go through, find where you find a match or keep a running total of something, things like that. It's the same basic idea. But I do encourage you to look at some of the simpler chunks of code here, understanding. All right. Now with the linear search, we're going to consider separately the cases where it's successful and you find the value you're looking for, and where it's unsuccessful and you don't find the value you're looking for. So on a successful search, the best case, you get really lucky and it's there in the first index. Ta-da, you find it right away, you're done. In the worst case, you have to scan all the way to the end, right? And if you're assuming that it's equally likely that that value will be found anywhere in the array, then on average, you'll have to search about half the array to find it, right? Sometimes you'll search a little, sometimes you'll search a lot, on average half. So the average for a successful search is going to be n/2, where n is the array size. In the unsuccessful search case, you always have to search through the whole thing. You have to check every record before you give up and say, oh, it's not there. So the best case is the same as the worst case. is always going to be n comparisons. Okay? Now, the one virtue of a linear search is that it's easy to understand and it's easy to implement as code. And if the arrays aren't too big, it's not really going to make much difference. It's only when the arrays get into like millions and billions of elements that linear search, you see a really bad slowdown. Okay, but you do eventually see it. Now, for a binary search, though, binary search essentially is like we do with a phone book. You look somewhere, start off somewhere in the middle, and if you've undershot, you go forward, and if you've overshot, you go backwards, right? So imagine for a second, imagine that this line is the phone book, okay? So we're going to label it appropriately. We'll say this is a list of phone book entries, okay? And the one we're looking for, we're going to do is just a tiny little dot here. We're going to mark him in green. He's right there. I need a bigger dot. Okay, that's where he is. All right, so that's the thing that we're looking for. Now, right off the bat, in this algorithm, I'm going to start at the middle, right? Because I don't know where this thing is going to be in the array. It might be, balanced more to one side or the other. So on average, I'm going to start in the middle. Right? This is not exactly a phone book. Now, if I open that, suppose I'm looking for, who am I looking for again? Susie Jones. I'm just going to label that with an SJ here. Now, suppose I start in the middle and I severely undershot. I go to like M there. And I say, oh, I overshot. So I'm going to go back. That was one comparison. I'm going to go about midway between the two. I'm going to go there. Okay. Now at this place, I've still overshot, right? Maybe this is, I don't know, JY or something. But with the algorithm, because I'm not a human who can understand, I'm a computer, I'm going to split this much, right? So with my first search operation, I eliminated this entire half of the phone book. I know it can't be there, right? One comparison, I got rid of half of the options. If I do it again, right, and I do something like here, and I say, oh, it can't be in this gap, once again, I have now eliminated about 3/4 of the possibilities, again, with just two comparisons. And in a very small number of comparisons, I can eliminate most of the rest. And each time I do a search, each time I do a comparison, I'm eliminating half of what's left because it's either got to be a match or on one side or the other. Now, after maybe about perhaps 15 or 20 searches, I find the correct entry, right? So basically the number of searches that are required is going to be log base 2 of n, essentially because each comparison removes half the options. So 2 to the 10th is 1,024. So basically out of every factor of 1,000, it'll take 10 comparisons to do it, right? So since 2 to the 10, I should do it the other way, huh? 2 to the 10 is about equal, there we go, about equal to 1,000. Every factor of 1,000 requires about 10 comparisons. Meaning, if the phone book has 1,000 entries, needs 10 comparisons instead of 1,000. If it has 1 million entries, needs only 20 comparisons, right? Which is much better than needing 1 million. If it has 1 billion entries, needs about 30 comparisons, right? So every additional factor of 1,000 only requires 10 more actual comparisons. So clearly, the size of the phone book can get really, really big. And as long as your data is sorted in this kind of orderly way along an indexed variable, it's very easy to find what you're looking for. It does not take that many comparisons as opposed to a linear search. Does that make sense? I hope it does. Yeah? Okay. Good. So let's talk about the algorithm for a binary search then. That's what a binary search does. So the way it works, first search the value in the middle. If X, the number we're looking for, is less than that value, then we search the middle of the left half next. If X is greater than that value, then search the middle of the right half next. All right, so we have an algorithm. This is why I haven't updated these slides, because the walkthrough is pretty nice and it would take me a while to replicate. So right off the bat, we're going to search in the middle index. So the low index is 0, the high index is 8. 8 plus 0 divided by 4, or divided by 2, is going to be 4, so that's where we search. Now, the number we're looking for up here in the corner, search 44, we compare 44 to that value at index 4. And we say, oh, 44 is greater than 38. So that means we've eliminated index 4 and every prior index as a possibility. It can't be in there because this array has been sorted. Right? So we've eliminated all that. So our next step, well, let's update the low index value. Now the low index value is 5. It can't be at an index below 5 because we've already ruled out all of that. So our low index is 5, our high index is 8. In Java, 5 plus 8 divided by 2 becomes 6, right? So we're taking advantage of that, of that truncation during integer division. So 13 divided by 2 is 6. Meaning 6 is the index we're going to check. Now, when we check that, we're going to see that 77 at index 6 is greater than 44. So what happens? Boom, we know it can't be at index 6 or greater. The highest index where it could be is 5. And so the low index is the same as the high index. When we add those two together, divide by 2, we get the mid of 5, and hopefully it's there. And in fact, we looked at it, and there it is. Boom, we got 5. And it only took 3 comparisons to do it. Right? If we're doing a linear search, on average, we'd have to do about 4.5 comparisons to find it if it were even there. Okay, so again, in a small array, you're not saving that much time with the binary search. You're saving a little bit, but it's probably not going to matter. It's only when arrays get big that becomes a significant issue. Now, unsuccessful search. Imagine we're searching for 45, which we can quickly eyeball and see that that's not in the array. So same process, we start at index 4, the midpoint there, okay? 38 was less than 45, so we know it can't be in index 4 or later, so our new low index is 5. And we do the same thing, our low index is 5, our high index is 8. We calculate the midpoint is going to be 6, so we compare 45 to 77. 45 is less than 77, meaning our new high index is now also 5. So what happens at this point? Well, at this point, we compare 45 against 44. And we say, oh, 45 is greater than 44. So clearly, the lowest possible index where this thing could be is index 6, right? Because it can't be in 5. But when we do that, we've squeezed out every possible space in the array. And in fact, the way that we know that is the low index is now greater than the high index, right? They've kind of flipped around and inverted because we've squeezed out every possible space in the array where this number could be hiding. And at that point, because we recognize that the low index is greater than the high index, we recognize that there are no more elements to show. And after only doing 1, 2, 3 actual comparisons of values, we've searched the entire array and said, nope, it can't be there. For a linear search, that would have taken us 9 comparisons, right? We would have had to search the whole thing. Okay. Now, if you're interested, here's the binary search code. Feel free to check that out, walk it, eyeball through it, whatever might be useful. But again, I'm not going to make you memorize this for the exam or replicate it on the exam, anything like that. Just, you might find it worthwhile to get a little bit of more understanding about Java. Okay, so binary search performance. In the best case, you find something right away. In the worst case, you do log base 2 of n, right? Because every operation removes half the search space. So every time you're cutting it in half, so as many times as you can divide n by 2, that's how many comparisons you might have to do. So log base 2 of n. The unsuccessful search, same thing, right? You're basically going to do every divide by half until there's no more space left in the array. So once again, as many times as you can divide the array by 2, that's how many it's going to be. So log base 2 of n. Now, quick comparison here, even for not very big arrays. If the array is 10,000, size 10,000, a linear search is going to require about 10,000 comparisons. A binary search might compare about 14, right? Even if you're doing this as a successful search, the linear search is going to be about half of that, still going to be about 5,000, right? 5,000 versus, you might on average lose one extra search requirement in the binary, so that might go down to 13. But yeah, even for moderately large arrays, and when you think about like how many credit card accounts a system might have to deal with, you know, or if Facebook wants to find you in their system and they have 2 billion monthly users, right, and you've got to look through a very large list, yeah, they're going to have some very big arrays to deal with. So it's important that they be sorted because the binary, right, search is so very, very, very much faster than the linear search. Okay, questions on any of that? All right, so key takeaways. Number 1, binary search, right? Obviously, number 1, know what a linear search and a binary search are, right? You should know what they are. Number 2, a linear search will eventually find whatever you're seeking, right? If the number's in the array, it will eventually find it, but much, much slower than the binary search in most cases. Okay, so I'm gonna add up here the algorithmic jargon. This is what they say, correct and complete. So the linear search algorithm, it is correct and complete. It will find you the answer you're looking for every time. It's just not terribly efficient. Okay. The requirement, though, the requirement for the binary search is that the data is already sorted along some index that is involved in the search, right? Like last name in a phone book, right? If the data is not sorted, then the binary search isn't going to work because it's built on the assumption that if you check that midpoint, you know that everything on one side or the other is automatically going to be invalid as a possibility. Okay? Questions on any of this at all? This makes lots of sense, I hope. Yeah, okay, good. Now, into sorting. So, there are 3 sorting algorithms we're going to cover. One of them is called selection sort, one of them is called bubble sort, and one of them is called heap sort. And we'll get to them. Okay, so our problem for sorting is if we have an array of n integer values, we want to arrange them into ascending order. The algorithms work the same if we try to do it in descending order. It's just, you know, for ease of exposition, we'll pick one or the other. Okay, and once again, whichever algorithm requires the least work to achieve the goal is the one that we're going to assume to be the best. Okay, let's talk. Well, first one, selection sort. So selection sort is a very simple algorithm that even, you know, bright children can come up with if you ask someone, hey, how should you sort this thing out, right? So imagine for a moment, imagine one that you lost a bet and you have to serve as a TA for a week during finals week. One of your tasks as a TA is to sort a big stack of exams or a big stack of scantrons, right? If I give you a stack of, say, 20 scantrons to sort alphabetically by last name, how would you do that? I say, here's some papers, get them back to me in 10 minutes. How would you do that?
It's like lay them out, like, so like if you see it like a Z or something, put it towards the end, or even like an R, like put it towards the end, but like that, like a long space that you could like
That's basically like the bubble sort that we'll get to next. Okay, so that's a perfectly sensible way to approach the problem. The selection sort would be this. You scan through the entire stack, find the one that's alphabetically last, and drop that on the table. Then you scan through the stack again, find the one that's alphabetically last for what remains of the stack, and drop that on top of the one you just dropped. And keep going through the stack each time, finding the last one and adding it in place. Does that make sense? I'm not saying it's the most efficient way to do it, but as we talk about algorithms being correct and complete, you will get the correct answer and you will have the, the scantrons in order. And if the stack is only 20, it's not that big of a deal, right? You'll get it done. So yeah, that's one way to do it. That's what selection sort is. So with selection sort, what you do, you start off with no part of the array being sorted, right? Is that top picture there. So you scan through the entire array, you find the smallest value. That smallest value, you swap into place with whatever's in index 0, right? Because we're trying to do this within the existing space of the array. We're not trying to use any extra memory. So you swap those two out, okay? At that point, you've sorted out the first index of the array. The rest of the array is not guaranteed to be in any sort of sorted order. So you do the same thing on what's left in the array, right? You take that 17 and you're going to swap it out with the 12 at index 4. And then those two indexes will be in order, right? And then you proceed with the rest of the array. So what happens after each pass? You have one additional element in the correct location, right? Every time you pass through what's left of the array, that's what you get. Now, I'm going to draw another picture, give you some mathematical insight. All right. So suppose we have an array that starts off, this is what we sorted at this point. In the next one, we sorted 2 elements. In the next one, we sorted 3 elements. In the next one, we've sorted 4 elements. The next one, 5, I guess. Bump you up a little bit. Then 6, 7, 8, 9. Okay? Now each time through, we're going to have, this first time through, I actually have to invert this. So let's do that. The first time through, we have to do 9 comparisons, right? We have to compare the value to every one of the other things in the array. The second time through, we have to convert 1 less, and we have to convert 1 less after that, and so on, right? Each time through, we've got one piece sorted, so we have to do less work each time. But what does this shape approximately look like? This shape here. If you were going to describe this shape to me, what would you say this looks like? And we don't have to do anything fancy. I mean, you don't have to say, whoa, this is an inverted quarter ziggurat. I mean, that's not really what we're looking for. What's that look like? What did I just draw in red? Triangle. Great. Now, what's the height on this triangle? How many times do we have to go through this process of scanning and putting one thing in its correct index? N times, right? 9, right. But n is 9. So in this case, we do it 9 times, but more generally n, the array size. And how many comparisons do we have to do on the first pass? Actually, n minus 1, right? Because we compare the first one, the first index to every other. So that's n minus 1. We could approximate that as n for large N, right? I mean, if n is a billion, we're not going to lose too much sleep calling it, 1 less than a billion, whatever. Okay, so if we know that this is a triangle and the two sides of this triangle are n, and it's a right triangle, not some, screwy other kind of triangle, what's the area of this triangle? which is, that's the general formula, but if the base is n and the height is n, yeah, n squared over 2, right? Area equals n squared over 2. That's how much work we have to do. We can express it as n squared over 2, okay? Because that's how many comparisons we have to do. As n gets bigger, the number of steps we have to do gets bigger, and the number of times we have to do those steps gets bigger, okay? N squared over 2. So tuck that away in your head for selection sort. Okay. And there's some code which you don't have to memorize, but it's there. Now again here, you know, they call it n plus 1 over, they have some different assumptions about what all this means, but still approximately n squared over 2 is where they end up with this. So that's fine. Now, next one is the bubble sort. So the selection sort, every time you go through a complete scan of what's left of the array, you take one element and put it in its proper position. But with bubble sort, every time you scan through, you have the possibility of doing multiple swaps. So we'll talk about this. So the way bubble sort works, you start at index 0 and you assume that nothing has been sorted out in the array. You compare what's in index 0 at index 1. If they're out of order, you swap them into the correct order, right? So because everything should be in ascending order. So smaller values get pushed toward index 0, higher values get pushed towards, you know, index n minus 1. So that first pass, we first swap out 23 and 17. We look again, we swap out 23 and 5. We look again, 23 and 90, they're in the proper order relative to each other. 90 is going to be bigger than anything else in the array. We can look at that. And so 90 is going to swap every time all the way through until at the end, 90 is in the last index. And we know that we've put 90 in its correct index, but we've also pushed some of those other values closer to where they belong, right? Because higher values are getting pushed one way, lower values are getting pushed the other way. Okay? With me so far? All right. Now here's some bubble code. That's fine. Now, bubble sort performance, on paper, it has about the same performance as selection sort, because each time we're only guaranteed to put one element in its correct location, right? That last highest value is always going to get pushed towards the end, and it's going to keep on rolling towards the end. The highest value will always get to the end. However, in practice, what happens is most data arrangements, you can manage to have some of the data closer to where it belongs. And if all of the data is very close to where it belongs, then you're not going to have to do that many passes. So again, on paper, yeah, selection sort and bubble sort, they're both going to be about n squared over 2, and for the same reason. But in practice, it's often less. Now, I'll give you an example why. So extreme bubble sort example. I'm just going to do a bunch of elements here. How appropriate. Okay. Now imagine that there is only one element out of place at this point, okay? And we're going to mark it here is where it should be, and where it actually is, we're going to mark over here. How many passes through with the bubble sort algorithm will it take to put those in their correct order, right? So I guess if blue has to be where green is, green has to be where blue is. How many passes would that take?
9.
1. We pass, right? We pass through with the bubble sort algorithm. Any pieces that are out of order, they swap. So after that first pass through, it's going to swap those two. Then the array will be in order. The next time it's going to scan through and say, oh, I didn't have to swap anything. I know I'm done. So if you had answered 2, I would have accepted that as well, right? But we have to have at least one pass through where something happens. Does that make sense? All right, so we're going to back it up a bit. Suppose blue is here. How many passes through will this take to sort the algorithm with bubble sort the array with bubble sort? Yeah, for the same reason, right? If these two are both out of order, then this one is going to get pushed forward, right? And this one will in some sense get pushed backwards, and then this one will be out of order and it'll have to get pushed back next time through. So if things aren't very far from their correct location, bubble sort can be tremendously fast, right? And one of the ways you can do this is if you segment a large array into what are called buckets, and you cap the size of those buckets as a certain interval, and then you say, yeah, you know what? Things are going to be pretty close to where they are. It's like having a bunch of smaller groups that are pretty easy to sort. You can do a quick scan through that and say, it's like if you're in a library, right? You're in a library and you're putting books away, and maybe you don't put a book exactly where it needs to go on the shelf, but it's pretty close. So when the librarian comes around, they can just scan through and say, oh, I swapped that one. It's really quick. It's much easier than if you have all the books completely jumbled. Then that's going to take a while. Okay, so, all right, we're going to talk about this. I'm going to do a quick summary before we move on, because this is a, okay, quick summary. Selection sort is simple to code and conceptualize, but quite inefficient. Takes a lot of work to sort a large array. Okay, that's that n squared over 2. Bubble sort is more difficult to invent, right? This is something that, you know, when people see it the first time, they're like, oh, hey, that's kind of cool. Yeah, neat. Okay, more difficult to invent and slightly better than selection sort in most cases, and in a few unusual cases, actually very fast, right? So that is when the data are very close to their correct positions, okay? In that case, bubble sort is actually really fast. So if you've structured your operation so the arrays are maintained that way, bubble sort can actually be useful. All right, but the next one we're going to cover in just a moment, heap sort, right? And it is one word. Heap sort is very difficult to invent, right? It was basically the product of a long project, let's say a long effort by many very smart people who invented progressively better algorithms, right? This is not the sort of thing, even if you're a really bright person, this is not the sort of thing you're going to slap together in your dad's garage without any real knowledge of how this stuff happens. It probably wouldn't occur to you. I wish I'd invented it, but you know, they kind of came up with this in the 60s before I was born, so didn't have a chance. Anyway, not saying I would have, but you know, first time I saw this, I was like, damn, that's neat. I wish I'd thought of that. Anyway, heap sort, very difficult to invent, but very, very fast relative to selection sort and bubble sort. And the key insight is this, how it works. Don't try to sort the entire array. Instead, try to break the array into sequences that are sorted, okay, as sort of a precursor. So first, rather, you know, selection sort and bubble sort, they try to put things in their correct location within the array. Heap sort doesn't do that. Heap sort says, you know what, first I'm going to arrange data in the array as a bunch of sequences that are all in the correct order, but they're going to be much shorter than the entire array, so it's a lot easier to build that structure. And from that precursor structure, it's relatively easy to sort the entire array. Okay, so those are just words. So now we're actually going to see how it works, and it's kind of neat. I hope you enjoy it. Okay, so remember, we've said that selection and bubble sorts both take n squared over 2 comparisons. Heap sort takes 1.5 n log base 2 of n. What does that mean? Let's suppose n is a billion. Okay? If n is a billion, then selection and bubble sort are going to take about 500 million billion comparisons. And that's a lot of work. That's going to take a while. Heap sort, n is still there, so we're taking 1.5 times log base 2 of n. Log base 2 of n, if n is a billion, is going to be 30. Because why? Because it's 1,000 times 1,000 times 1,000. Every factor of 1,000 adds on 10 to the log base 2. What's 1.5 times 30? What?
45.
45. So heap sort, instead of taking 500 million billion comparisons, takes 45 billion comparisons, right? We're literally improving the efficiency by about a factor of 10 million, okay? It's pretty incredible. This is like one of the algorithms that's behind managing all the, big data operations we have these days. So it is very important. Now, there are a few other algorithms that are similar. There's one called quicksort, for example. They have their different pros and cons. They work in about the same speed, but the advantage of heap sort is it doesn't require any additional memory space. All the data is managed within that same structure. Quicksort can be a little faster, but it also requires duplicate array structures, so it requires more memory space. Anyway, okay. So a heap is a data structure. What we'll cover here, the little numbers on top of the bubbles, those are the array indexes, okay? So we start at 0, then there's 1, there's 2. They're arranged as a tree, but obviously when they're stored in the array, they're just, they're just a line of numbers. But this is helping conceptualize it. Index 0 is what's called the root node. And if you flip it upside down, right, it becomes very obvious why it's called a root. The numbers below each node, those are its children. So over in index 2, we have the 44 at the right. Its left child is 5, its right child is 6. Okay? So that's the notation. We have a root node, we have parents, we have children. Anybody notice anything about this heap structure? Anything jump out at you? You say, hey, that's kind of, anybody notice anything about it?
The child nodes are always smaller than the parent nodes.
Yeah, that's true. That is a defining quality of a heap. Okay, that's one of them. It's not the only one. Okay, but good. Yeah, so if you look, remember when I said that we break apart the array into sequences that are ordered, all of those sequences, if you start at the top and go down to any n child node, what's called a leaf node, it's always going to be sorted. So if you go 0, 1, 3, 7 all along the left line, it's all in descending order. If you go 0, 1, 3, 8, again, all in descending order, right? That's the key insight behind the heap, is that you don't have to sort the entire array. You can just sort it into threads like that are ordered. And if you know that that's true, then we have some real magic. If we know that all these threads are ordered, the top value must be up here, right? We know this because it has to be. And we also know that if we take this away, one of these must be the next highest one, right? So we've taken, without sorting the entire array, we've built a precursor that is much easier to sort. All right, so we'll get into the algorithm. So first of all, heap constraints. When you're designing a heap, there's a couple constraints that have to be followed. The first one is the structural constraint. So if you have a heap with n nodes, they're going to occupy the array indexes numbered 0, 1, all the way to n minus 1, right? So in our picture, what we're doing is each node can have up to 2 child nodes, and they start with the left, right? So 0 has the child nodes 1 and 2, 1 has the child nodes 3 and 4, 3 has the child nodes 7 and 8, right? We fill up each level left to right, and we don't add child nodes to another one until the one on its left is full. So we don't add any child nodes to 5, for example, until we've added 2 child nodes onto 4. That's the structural constraint. So again, because all of the array indexes are numbered that way, This ensures that the contents of the heap correspond correctly to the array indexes. Second part is the value relationship constraint. So basically, all parent nodes have higher numbers than their child nodes. And it's an easy thing to remember, right? Because what is one metaphysical certitude we know about parents and children that's related to numbers? Yeah, but in real life, what do we know about parents and children? Is it possible to do some backup to the future bullshit and be younger than your parents? Oh, older than your parents, sorry, yeah. Is that possible? No, it is not, right? Parents have to be older than their children, otherwise, how's that even gonna work, right? Same thing, so if you just think about those as ages, the child node is gonna have a lower age than the parent node, duh. Okay. Oh, I don't know about that dude who's 77 and got like kids in 20, so good for him, but whatever. Okay, anyway. Now, structural constraints, these are correct heaps. That's fine, but we're gonna look at the deviant ones. We're gonna look at the non-heaps. So this first one on the lower left, why is that not a heap? This one, why is that not a heap? Right, this child node belongs here, doesn't it? Okay, everybody see that? Okay, what's wrong with this heap? What's wrong with the middle one? Looks like a mutant wishbone, doesn't it? What's wrong with that one? It's a letter F that's tipped over. Why is that not a heap?
It was second level.
Yeah, there's empty space there, right? This child node belongs here, and these two child nodes belong there, and this level up above should be completely full before you add anything there, right? Okay. What about this one? What's wrong with that one? Yeah, these two child nodes are in the right level, but they belong as children of that parent node, right? Not this one, because we fill out the levels left to right. Okay? So yeah, that's the structural constraint, right? So if you want to express it as a couple of simple rules, number one, so heap sort structural constraint rules. Number one, each level must be full before the next level starts, right? You got to fill up the top one before you fill the one below. Number two, child nodes are added left to right on each level. And number three, parent nodes can have no more than two child nodes. Okay? You can come up with other ways to express that if you want, but that's the idea. You fill out each level before you start a new level, you add the child nodes left to right on a level, and each parent node can have up to two levels, have up to two child nodes, and that's it, right? So once every node on a level has two child nodes, it's time to start the next level. Okay. Now, value relationship constraint, that's an easy one, right? We just look at there and see, oh yeah, those numbers are out of order, right? Because the child nodes have to have a lower number than the parent nodes. So, fine. And there's not much else to say about that. Okay. Now, does that all make sense? Are you guys ready for the heap sort algorithm? All right, this is one of those things. There is partial code for it, but if you look at this is complex enough they make it pseudocode. It's not actually, so a lot of that green stuff is going to be, that's not actual code, that's just expressing what the code should do. So it's not code proper. So the heap sort works in two stages. First of all, we construct the heap, right? We build it in a way that we have an array of unsorted data. We take that unsorted data, turn it into a heap, which is to say partially sorted data. Once we have the data partially sorted in that heap structure where all the threads top to bottom are sorted, then it becomes very easy to take that data and turn it to fully sorted. So we're going to go with the construction phase first. Okay. I'm going to do the before picture. All right. Now, in the construction phase, we have some unsorted data, and the first thing we're going to do is check and see if things look correct. And the way we check, we do an eyeball and we say, okay, yeah, this seems to match the structural constraints, right? That's fine. It matches the structural constraints. We don't have to worry about that. Second, we have to check the value constraints. And so what we do is for every parent node, we compare it to its child nodes. And if the child node is out of place, we swap out the parent with that child, okay? So we look at 90 here. Is this all good relative to those two? Is 90 greater than 84 and 77? Yeah, okay. What about 5? Is 5 greater than 44 and 38? How do we make that right? Swap 5 and 44, right? So we swap it with the greater of its two children. Very good. We're going to do that. Move in here. And remember, we keep the indexes where they are because that's where those things are going to go. Do transparent selection. Okay. Okay, so we've done that. That's good. Now, what about 17? Is 17 incorrect? Is that in a correct spot or not a correct spot? No, why? That's right. 17 is greater than 90. So we got to take 90 and put it up there. But what happens? We roll down 17 to index 3. We do the same thing, right? Is 17 in the correct spot at index 3? No, we got to do the same thing, right? We got to swap it back. Yeah, so 84 goes up there, and 17 can reside down here. Okay? Now we only have one left to do. 23, right? Because we've done 1, we've done 2, we've done 3. We check number 0, index 0. Is index 0 correct? No, it's terrible. So what do we do? Yeah, basically we let it roll downhill, right? So we take 90, swap it with 23. When we compare 23 with 84 and 12, we know, oh, you got to move 84 up here. And we compare 23 to 17 and 77. You got to swap them out. Okay, and at that point, we have verified that every parent node is correct with respect to its child nodes, right? We know at index 2, we're good. We know at index 3, we're good. We know at index 1, we're good. We know at index 0, we're good. We have a heap. That's nice. All right, now if I take this image and I compare it, all right, I'm just actually going to lift the one from the slides here. Kind of looks the same, right? As you would expect, because this is a heap, and we're following the algorithm. Okay, so that's the construction phase, right? So the construction phase, again, take the unsorted array data and partially sort it into a heap. Okay, that's what we do with the construction phase. Now, the next part is the extraction phase. In the extraction phase, we know that the root node must have the highest value and consequently belongs in the last available array index. Okay? We know this. In our old thing, right, we had that 90 there. So our root node here, this is the extraction phase. We first say, oh, 90. That's at the root. It's at index 0. I'm going to swap it into index 8. So I'm going to swap out 90 and 23. But 23 will no longer, index 8 will no longer be part of the heap. It'll be part of the sorted part of the array. Okay? And then I'm left with 2 subheaps over there. So this 2, 5, 6, that's one cluster. That's going to be a heap. And this other part, 1, 3, 4, 7, that's also going to be a partial heap. So I have to figure out, where this 23 is going to go. I basically roll it downhill the same way as I did in the construction phase a minute ago. All right, so we're going to do that. So this happens iteratively, basically over and over, until no array indexes are still unsorted. Okay, so over time, we're going to know the root node has the highest value. We removed, after removing the root node, we rebuild the heap, right? Because the value in the last index must be out of place in the root, right? We know when we swap out 90 and 23 there, 23 is less than 77, it's less than 84. We know it's got to be in the wrong place, right? So we got to let it roll down into its correct place. But the fact that we don't have to search through the entire array, we just have to search through the height of the array, makes this a lot faster. That's where the speed gains come in. We're not trying to find the absolute best place for 23 relative to the entire array. We just want to make sure that what we're working with is still a heap. Okay, so I'm going to walk you through the extraction phase, and I promise you it's going to be just as fun as it sounds. So, first things first, right? What do? We take out the root, put it in the array. Take this last value. We're initially going to drop it into index 0, but we know it can't be there. We're going to compare it to the two children, right? So what happens? Swap it with the greater of the two children, 84. So 84 becomes the new root, and we let 23 roll downhill. What do we do at index 1? Can't stay there. Swap it with 77, correct. So we bump that back there, okay? Is 23 good index 3? Yeah, sure, looks good. Okay, so that's our new heap. Is this a heap? Yes, it satisfies the structural constraint, right? This third level is full up, this one has started, and it satisfies the value constraints, which we just implemented. And we know we don't have to look at the whole rest of the heap, we just have to look at that one little thread, right? Because that's the only part that changed. So what do we do now? Same thing you do with any root, right? You pull it out, put it in index 7, take the last child, put it at the root. Well, we know 17 can't stay there. What happens? Swap it with 77, right? Swap it with the greater of the two children. Can 17 stay in index 1? No, right? We got to swap it out with index 3. Can 17 stay at index 3? Yeah, because we've rebuilt the heap, right? So we're all good. Now what happens? What do we do now? Pull out the root, right? Pull out the root, put it in the array. Take the last child, put it in the root. Whoop. Ah. But we know it can't stay there, right? Because it was a child, thus another value must be greater than it. So what do we swap it out with? Yeah, the greater of the two children, right? So that goes index 0. Is 38 okay in index 2? Yeah, because it's greater than the one child there that's left, right? Fine. So now we have a heap. And what do we do when we have a heap? Pull out the root, right? Anytime we see a heap, we pull out the root. Pull out the root, put it in the array, take the last child, because remember, we're swapping 44 into index 5. Take the child, put it there. Can't stay there, can it? Where's it going to go? Probably not. If we do it with index 1, if we swap it with 23, what happens? 23 is less than 38, right? Yeah, so we don't want to do that. I know, you were just trying to trick me there. Okay. That's all right. Okay, so we do this. Do we have a heap? Yes. Yes, we do. We satisfied the structural constraint. We satisfied the value constraint. And what do we do with the heap? Take out the root, put it in the array. All right, so boom. And then we take the last child. Yep, put it in the root. Okay, can 12 stay in the root? It cannot. Sorry, 12. Same thing. So 12's got to roll downhill. Swap it out with 23. Can't stay at index 1. Swap it out with index 3, right? And at this point, do we have a heap? We have satisfied the value constraint. We have satisfied the structural constraint. So this is a heap. And therefore, take out the root, put it in the array. Correct. That's what we do when we see a heap. Okay. And the last child goes into index root, but it can't stay there. So we swap it out with 17, right? Swap that out. And do we have a heap? This is a heap. We've satisfied the structural constraint, right? Levels are packed left to right, no more than 2 nodes per parent. We've satisfied the value constraint. 17 is greater than either of its children. This is a very small heap, but is still a heap. And by now you must surely know what we must do. Take out the root, put it in the array. Okay, we take the last child at index 2, because that's what we swapped out 17 with. Can't stay there. We let it roll downhill. Is this a heap? This is a heap. It satisfies the structural constraint, right? We've started filling in the second level left to right. That's fine. It satisfies the value constraint. 12 is greater than 5. So what do? It's a heap. What do we do? Take out the root. And since we've just swapped 12 with 5, we're done. How about that? Okay, so that is the heap sort algorithm. And by following that algorithm, you can sort even large arrays amazingly fast compared to other options that are simple to understand in code. Okay, so that was kind of neat, I hope. Anyway, so that's it, right? And there's some code, Now, heap sort performance. This is basically a proof of it, talking about the number of comparisons. So essentially, there's 2 parts. Every time you're rolling one of those values downhill, you're essentially rolling it down the height of the heap. And you do that 1 time for every log base 2 of n. And constructing the heap is also going to take some time. And again, for every parent node, you're going to have to potentially roll them downhill. Okay, so essentially, n over 2 rebuild steps in the construction phase. Each one of those is going to take, not very many comparisons. So when we combine those 2 things together, right, the rebuild step is going to be n divided by 2 times log base 2 of n, and the construction? No, that's the construction phase. N over 2, because each one is going to have to roll down, a certain length, but not the whole way. And the other part, the rebuild, is going to each rebuild step is going to take no more than k comparisons, but we have to do it n times, right? We have to do it once for every value that we're swapping out, but roll it down the height of the array, the height of the heap. So when we add those 2 things together, 1.5n log base 2 of n. Now, I'm not going to ask you to derive this. I'm not going to ask you to discuss it, right? This is not really a math class or an algorithm class as such. So key thing about heap sort, key takeaways. Number 1, the heap sort is way, 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 way faster than selection sort and bubble sort for large arrays, except for some oddball special cases, right, which we've already discussed. So for example, in bubble sort, if there were only like 2 pieces, 2 array elements out of order and they were next to each other, sure, that would be super fast, right? But that's a really oddball case if you're talking about a random array of data. Okay. Number 2, heap is a data structure with 2 requirements, right? Number 1, I'll say a structural constraint, which we've discussed, and B, a value constraint, which we have already also discussed, right? That whole parent-child age thing, okay? Number 3, heap sort algorithm itself, not in stealth, itself has 2 phases. Construction phase, which takes the unsorted array data and arranges it as a heap, and B, the extraction phase, which iteratively removes the root node from the heap, places it in the correct array index, and then rebuilds that part of the heap. Okay, that's the takeaways. Questions on any of that? All right, so again, for heap sort, I'm not going to make you walk through steps of the algorithm, but I will say for selection sort and bubble sort, usually written as one word, bubble sort, expect to predict the results of one pass through with either algorithm. Okay, so if I give you an array and I say, do one pass through with selection sort, what's it going to look like after you do one scan through the array, right? You swap out the lowest value with wherever the other one is. And likewise, if I tell you to do the bubble sort, you go through and you swap everything along the way, and what's it going to look like on the other end of that? Okay? All right. That's all I got for today then. Thursday is going to be a review session. I don't know, questions for me on any of this stuff? Nothing? All right, that's all I got then. We're all free to go about our business, I guess. It's been a hoot.